We're Team 15 and our project is the Modularized Robotic Arm. The team consists of Kevin Bradshaw, Fuhua Song, Yuan Tian, and Zhengshua Zheng. The Modularized Robotic Arm is a proof-of-concept system that's designed and constructed to create a better user interface for controlling emergency situation robotics. This is done by wirelessly tracking a user's arm movements and producing that data to a robotic arm. The field of automated robotics is constantly improving. There are certain high-stakes situations where a person's instincts and perspectives will be superior to that of the current automated processes. The purpose of this versatile robotic arm that we're building is to aid in emergency situations in which the human senses and control are critical without having a physical person present. To be able to achieve this project is divided into 5 subsystems. This includes power, control, software, hand tools integration, and communications. This diagram shows the system overview of all the major components required. This is our first working prototype of this concept. As you can see, the robotic arm itself is an independent system of the controls. There are still several power components such as a regulator and a few power MOSFETs that need to be added to this prototype in order to make it fully independent from the control. The power subsystem is divided into 2 external power supplies. One is a 12-volt 20 amp-hour battery that is connected to all the motors of the arm. The other is a 5-volt 4.6 amp-hour battery that is connected to the Raspberry Pi 2, which in turn powers its peripherals. Although power is not an emphasis on this project, every motor draws a significant amount under constant load and needs to be accounted for. This is an example of how the elbow motor was tested. Each motor was tested individually for the current draw at a 4-volt DC input. With a robotic arm that consists of 5 motors, 3 different positions for each was tested. This table depicts this information for each motor running individually on the power supply. In order to be able to test for long periods of time, the runtime of the entire system was overcalculated to a 12-volt 20 amp-hour supply. This supply is regulated through a buck converter. Next semester, the goal will be to run each motor together with a few power MOSFETs. The control subsystem is primarily software in which a simplified flowchart can be seen here. This is all based on the mechanical output testing of the arm. This subsystem consists of correctly portraying the angles of the arm needed to match the data from the Connect. This means that the PWM duty cycles for each motor is mapped to specific angles. 3 different positions for each motor were tested for pulse ranges. Each motor has particular range of duty cycles that works for the ranges of motions of the user. This is an example of one of the tests conducted. By sweeping the PWM signal, we can see the full range of motion for the elbow motor. The rest of the test results can be seen in this table. Each motor was swept through the 12-bit PWM resolution with a chosen step size. As you can see, this FLTK window is developed as our system user interface. It currently only has 2 buttons that can start and terminate the entire system. After start is pressed, the system will check the user sampling range, then obtain the individual position and store that information for later use. After this step is done, the system enters the mimicking stage in which skeletal data is obtained and processed continuously. The data is used to map the user's arm movements to the robotic arm movements. Now you can see the real-time coordinate data of the user's primary joints. This data is further processed to obtain the angle representations for the 3 servo motors on the robotic arm. Angle data can be directly used to define the duty cycles. As for the angle difference data you see over here, we calculated them by taking the average of 3 data points and then taking the difference between the previous angle and the next angle. The angle difference data is used to define the frequency which determines how quick the robotic arm moves.
In order to remote access the Pi, we will begin by SSHing through PuTTY. Once connected, we will use socket communication in order to allow for packages of data and information to be transmitted. Socket communication relies on establishing a client and a server. In this case, the Raspberry Pi will serve as the server, while the computer will act as the client. Once connection is established, commands can be sent through the Pi. For example, here I am getting a simple package of data in text. This can also be established for motor control and feedback later down the road. We can also use the Raspberry Pi to get visual feedback. For example, here I am remote accessing a camera module mounted on the Pi. As you can see, I am getting feedback.
Most of the parts of the hand were built by 3D printing. The fingers will be able to move with a stepper motor that rotates the middle shaft that will be built later. The fingers will close while the stepper motor rotates clockwise, and open while the stepper motor rotates counterclockwise. This semester was focused on the wireless control of the stepper motor.
This is the control flow chart for the hand tools integration. The Myo reads user gestures and sends instructions to the laptop through Bluetooth. Then the laptop sends this information to the Raspberry Pi. Afterwards, the Pi sends movement instructions to a stepper motor driver which rotates it according to the proper gestures. On the server side, the code is written in Python. The program can read keyboard inputs to execute motor rotation after the user presses the designated keys. After running it, if the user presses a lower or uppercase A, the stepper motor will rotate clockwise in 270 steps. If the user presses a lower or uppercase D, the stepper motor will rotate counterclockwise in 270 steps. For the client side, the code is written in Lua on the Myo. It allows the Myo armband to read the user's gesture and control the keyboard in order to construct the communication between the Myo and the Pi. When the user makes a fist, the armband reads it and sends the instruction of pressing A to the laptop. When the user spreads their fingers, the armband sends the instruction of pressing D to the laptop.
We've made great progress building and testing the prototype. The next step is to sync the data from the Kinect and the Myo through the communications and into the robotic arm. Thank you.